Have you ever tried to remove iron filings from a magnet? Not easy. And of course, the stronger the magnet, the stronger the attraction. Appreciating this relationship between attraction and the energy needed to overcome the attraction is central to the ionization energy. This is Real Chem. Understanding ionization energies will require resilience for all of us. This is because it draws from quite a few different areas of knowledge. But know that everyone faces a challenge with this topic, and so be easy on yourself if this doesn't click right away. Stick with it. Use the people and resources around you to help you. You'll get there. Let's explore. I love learning about the periodic table. For one, it can be used to predict what type of cation or anion an atom would make. And because of that, we can also use the periodic table to predict how easily atoms will be converted to ions by the energy changes it takes to do this, which are periodic properties like atomic size. To form a cation, an atom has to lose an electron. The energy for this is called the ionization energy. It always requires energy to pull the negative electron away from the positive nucleus. So, all ionization energies are endothermic. How easily an electron can be removed from an atom depends on the strength of its attraction to the nucleus. So, two factors matter here. The distance between the electron and the nucleus, so the farther away, the easier it is to remove, and the effective nuclear charge. The larger the charge, the harder it is to remove. Let's illustrate this with two elements, beryllium and magnesium. Beryllium, or Be, has 4 electrons, 2 in the first shell and 2 in the second shell. To ionize beryllium, we need to remove an outer shell or valence electron. A valence electron in beryllium is attracted by the +4 charge of the nucleus, but a charge of -2 from the inner shell electrons shields the valence electrons from the +4 nuclear charge. This results in an effective nuclear charge, or Z effective, experienced by the outer electrons of +4 -2, giving +2. Beryllium has an ionization energy of 900 kilojoules per mole. We'll use this as a reference point. Next, let's look at magnesium, or Mg. Magnesium has 12 electrons, 2 in the first shell, 8 in the second shell, and 2 in the third. A valence electron in magnesium is attracted by the +12 charge of the nucleus, but a charge of -10 from the 10 inner shell electrons shields the valence electrons from that +12 nuclear charge. This results in an effective nuclear charge experienced by the outer electrons of +12, -10, giving +2. So ionizing magnesium requires pulling a third shell electron away from an effective nuclear charge of +2. The valence electrons in magnesium are further away from the nucleus than those in beryllium, but both have the same Z effective. This means a weaker attraction is found in magnesium than beryllium, and therefore lower ionization energy. Magnesium has an ionization energy of 730 kilojoules per mole, significantly less than the 900 kilojoules per mole for beryllium, which confirms our prediction. This reasoning holds for other elements in a given group. So in general, the ionization energy increases as you go up a group. Atoms get smaller as shell numbers go down. Going across a row, the effective nuclear charge increases, but the valence electrons are in the same shell. The higher the nuclear charge, the harder it is to remove an electron. There is a lot going on here, and so don't worry if this hasn't clicked immediately. Don't lose sight of the most basic principles. All we are doing is rationalizing why some atoms take more or less energy to pull an electron away from its atom. Just like those iron filings on the magnet, it takes more energy to get them off if the magnet is strong. So explore and remember to have fun.